Hey class, today we're going to be doing section 4.16 in AP Stats, which is talking about probability models. We're going to be doing Bernoulli trials and binomial distributions and geometric distributions for our probability. So let's start by defining what a Bernoulli trial is. Situations that have the characteristic below are called Bernoulli trials. So each trial has only two possible outcomes. Either we have success or we have failure. The probability of success remains constant throughout all the trials, and the trials are independent. So we have two types of Bernoulli trials. We have geometric distributions, which we are going to go over first, and then we're going to do binomial distributions. So these are our two types. Geometric distributions are Bernoulli trials that stop after the first success. If X is the number of trials until the first success is observed, and P is the probability of success, then the expected value of the number of trials until the first success is observed is going to be 1 divided by P. And our standard deviation is going to be the square root of 1 minus P divided by P squared. So note 1 minus P is the probability of failure, because P is the probability of success. So 1 minus P is the probability of failure. All right, so suppose that 30% of the students who drive to campus at your university carry jumper cables. Your car has a dead battery and you don't have jumper cables. So you decide to stop students who are headed to the parking lot and ask them if they have a pair of jumper cables. You want to know how many students you would need to stop before you find one with jumper cables. So the first thing we have to do, and this is going to be kind of the first time we've really seen this in AP Stats. This is a little bit new, but it'll carry on through the rest of stats. We have to verify a certain set of conditions before we can use a geometric distribution and use these formulas. So the conditions, there's 4 conditions. The first one is, so we have the 3 conditions. So condition 2, 3, and 4 that you see here are those conditions of all Bernoulli trials. And then number 1 is specific to geometric distributions. So number 1, trials stop after the first success. And then I want to put context in there. So set of cables is found. 2, each trial has 2 outcomes, cables found or not. Trials are independent. So one person having cables or not doesn't affect the chance of the other person having cables. And the probability of success, which is finding cables, is constant at 0.30. Now, I have a nice, fun little way to remember these, and it's tri-tip. Tri-tip. So tri stands for, and let me get my highlighter here, trials. And then T, that's the wrong T. Each trial has 2 outcomes. So T for 2. Trials are independent, and the probability of success. So we have tri and then TIP, tri-tip. So just kind of a nice way to remember. There's going to be a lot of different things we're going to learn in AP Stats with a lot of different conditions. So it's nice to have little things that help our memory. So X is the number of students you stop to ask for jumper cables. Find the probability that the first student is the 4th person you ask. So the probability that X equals 4. Well, that means the first person I ask doesn't have cables, which is a 0.7% chance. These are independent trials. So that's not going to affect the next person. It's going to have the same probability of failure. The next person does not have cables. The next person does not have cables, but the 4th person does. So here's my probability, or you can write this as 0.7 cubed times 0.3 to the 1 power, and that's going to be 0.103. Find the probability that one of the first 3 students you ask has jumper cables. So this one's a little trickier. So probability that one of the first 3. So that's going to be the probability that X is less than or equal to 3. So either the first person has cables or the second person has cables or the third person. So if the first person has cables, we have a 0.3 chance of that happening. Or, so plus, the first person could not have cables, but the second does. Plus, the first two don't have cables, but the third does. So we would add up all these, we get 0.657. So you have a 65.7% chance that one of the first three people you ask has jumper cables. That's kind of nice. All right, and the last one, find the probability that more than 5 students, so probability that X is greater than 5 must be asked. Now here it gets really tricky. We can't just do this the same way as we did the other ones because more than 5 could theoretically take forever. It could be 5 or 6 or 7 or 8 or, and you could just keep going. So we have to use the complement of this probability in order to answer this. So the complement, so we've got 1 minus the probability that X is less than or equal to 5. So notice it said more than 5, so it doesn't include 5 initially. So when we do the complement, we want to include 5 and anything less than that. So that's going to be 1 minus the first one having cables. And I'm going to put parentheses, so more than 5. So I'm going to put parentheses around this. Minus, or the second one having cables, or the third one having cables, so 0.7 squared times 0.3, or the fourth one having cables, third times 0.3, or the fifth one having cables, so 4 failures and a success. And then we need to close our parentheses there. And remember, you're subtracting that whole thing, so really it's minus in front of each one of those if you distribute that negative through. Now there is, and I'm going to go over one more example like this on the next page. There's actually a way we can use the calculator. There's a calculator function that'll give us the answer to this, which is really nice. So we get 0.168. All right, let's go to the next page. We're going to do another example, and I'll show you some of the calculator work here. Bo is a dog that loves to play catch. Unfortunately, he isn't very good, and the probability he catches a ball is only 0.1 or 10%. Let X equal the number of tosses required until Bo catches a ball. A, verify the conditions. Now, the problems usually don't tell you to verify the conditions, so you have to realize that this is a geometric distribution, and you have to remember to do the conditions even if they don't ask you to. So be really careful. So again, we've got our try tip. So trials stop after first success. Trials have 2 outcomes, T for 2. Trials are independent, I, and the probability of success is constant. Now notice I also put context in each one of those. So you can see those in parentheses there. It's important to add context into our conditions. Find the probability that it will take exactly 2 tosses for Bo to catch the ball. All right, so P is X, so probability of X equals 2. Well, if it takes 2 tosses, then the first toss he misses 90%. The second toss, he gets it, so we get 0.09. Now, there is a way we can do this in the calculator, and I know that this one really wasn't that much work, so it's kind of silly to use a calculator. It's actually probably more work to use the calculator function in this, but I'll show you how it works. So it's called Geomet PDF. And then we have, so if I go to the calculator, and hopefully your calculator gives you input prompts because it makes it so much easier. So if we do second and the vars button to go to distributions, and then press the up arrow to go to the bottom of the list, you're going to see geometric PDF and geometric CDF. We're going to use both of these. So in this one, because X equals 2, we're going to use the PDF value. So enter, and then my probability of success is 0.1. So P represents the probability of success. My X value equals 2. I want X equals 2. And then I'm going to hit this. So first, before I hit paste, I'm going to write 0.1 and put P underneath it, and 2 and put X underneath that. Remember, we always want to label our inputs if we use our calculator functions. And press enter, and I get the same answer. So you can do this either one of 2 ways. Personally, I don't usually use geometric PDF function because it's actually more writing than just writing out the probability. And I like when my students know how to calculate the probability and they understand the concept behind it instead of just trying to put stuff in a calculator. Now find the probability it will take at least 4 tosses. So this is another one. So probability of at least 4 is x is greater than or equal to 4. This is another one where theoretically that could take forever. We have to use the complement. So 1 minus the probability of, what's the opposite of greater than or equal to 4? Well, it's going to be less than or equal to 3. Because 4 was included in this case, we want to not include it in the complement. So if I do this right, the same way we were doing it, it'd be 1 minus, and then grouped parentheses. They could take, so if it only takes 1 toss, that's a 0.1%. Or he could miss the first time and make it the second time. Or he could miss the first 2 times and make it the third time. Oops, 0.1. All right, so, and I can plug that in my calculator. And I get, so the probability that x is greater than or equal to 4, because remember we're subtracting that from 1, is 0.729. Now, if I want to use the calculator function, this is going to be a geometric CDF. So C stands for cumulative. So you're adding all the way up to a certain value. So 1 minus the geomet CDF. Okay, so let's go in our calculators. Second, vars, up, and then geometric CDF is that very bottom one, hit enter. Now we have still a P and an X value. So still the same inputs as before, but C stands for cumulative. So it's gonna go everything up to including the value we put in. So probability of success is 0.1. I want 3, because I want all the way up to 3, including 3. So 0.1 and 3, and I get 0.271. Oops. Oh yeah. And then I have to subtract that from 1. 1 minus, I wrote it down. This one. There it is. All right. So 0.729. So be careful. We know we have to subtract from 1. Don't forget. All right. Now remember, if you do use the calculator functions, you need to label your inputs. And you still have to write your probability statement. I wrote it at the top, but I probably should have written it down here too. Okay. Find the probability that Bo catches the ball on one of his first 3 tosses. So probability that he catches it on one of the first 3 tosses. So this is going to be the probability that x is less than or equal to 3. So we actually already saw this. This is our geometric CDF function, 0.1 and 3. So we already saw this. And that was 0.271. We could have also just taken the fact that the opposite was calculated in the last problem. So I could have just said that this equals 1 minus 0.729 and used my work from the previous problem, since we already showed that work. So either one would have been fine, or you could show the whole formula. All right, and last one, find the expected number of tosses until Bo catches the ball. So this is where the expected value equals 1 over P is going to come in. And then our standard deviation of x is the square root of 1 minus P divided by P squared. All right, so expected number of tosses until he catches the ball, 1 divided by 0.1 is going to be 10. And that kind of makes sense. If there's a 1/10 chance of him catching the ball, or a 10% chance, then you would expect there to be about 10 tosses and then he would catch the ball. Now, that's a theoretical expected value, of course. And then standard deviation of x is going to be the square root of 1 minus 0.1 divided by 0.1 squared. So we get the square root of 0.9, the failure, or probability of failure, divided by 0.01, which is 9.487. And then we probably should put tosses so that we have context here with our answers. All right, next page. This is our last page, and we're going to talk, so moving from geometric distributions to binomial distributions. Binomial distributions are also Bernoulli trials, but they have a fixed number of trials. So that's the only difference between them. The probability of k successes out of n trials, where p is the probability of success, and this gets a little confusing here, But that equals, so the probability that X equals K, so probability of K successes, is going to be N choose K. So this is NCK. It's combinations. It's the number of ways we can the number of ways we can choose K things out of N total items. And I'll explain that a little bit in a second. P to the K power times 1 minus P to the N minus K power. So remember, 1 minus P is the probability of failure. If K is the number of successes, N minus K is the number of failures. And let's see. So again, this NK, it's not a fraction. I'm not just forgetting my fraction bar. It's just notation, is NCK. And this equals the number of ways you can have K successes out of N trials. I will give you an example. Mean and standard deviation of a binomial distribution. The mean is N times P, and the standard deviation is the square root of N times P times 1 minus P. All right. A basketball player makes 85% of all free throws she attempts. Let X equal the number of free throws made among the next 12. And I'm going to check, sorry, I'm going to pause, or not pause the video, but just really quick, I wanted to show you on our formula sheet for AP Stats, the formulas for expected value and standard deviation of binomial and geometric distributions are on our formula sheet. So you don't need to memorize these. You just need to know how to use them, which is nice. All right, so we need to verify that all the conditions are met for binomial. So it's still tri-tip. The only difference is that instead of the trial stopping after the first success, here we have a fixed number of trials. We have 12 shot attempts. And then, T for that there are only 2 outcomes. We can make or miss the shot. I for trials are independent, so each shot attempt is independent. And P for the probability of success, which is making the shot, is constant at 0.85. So tri-tip still holds, which is nice. Find the probability she makes 8 of her next 12 free throws. So the probability that X equals 8. 8. Now, this is where this 12 choose 8 comes in, because making 8 of her next 12 free throws, she could make the first 8 of the next 12, or she could miss the first 4 and make the next 8, or she could make 2 and then miss 1, and then make 6 and then miss 1. And there's so many different ways that you can make 8 shots out of a 12 shots. And so this calculation, 12C8, gives us the way to find. So let's just do that part really quick. So if I hit 12, and then I go to math, and I go over to probability, there's NCR. So 12C8 equals 495. Excuse me. There are 495 ways that she could have made 8 shots out of 12. So we have to think about all those possibilities in our calculations. Luckily for us, we don't actually have to think about how many it is. The calculator does it for us. We just have to know our formula. So 0.85 to the 8th power times 0.15 to the 4th power, because she makes 8 shots. So 85% probability of making a shot, there's 8 of those. And 15% when she misses the shot, and there's 4 of those, makes up the 12. So that's going to be, so 495 times 0.85 to the 8th times 0.15 to the 4th, I get 0.068. So she only has a 6.8% chance of making 8 shots. All right, now there is a calculator function for binom PDF. So if I have 12 trials, probability of success is 0.85, and my X value is 8, that's going to give me the probability. So let's just write that in. binomial PDF because it's just x equals a number. And I had 12 was my number of trials, n. 0.85 was my probability of success, p. And 8 was my x value. I get 0.068. So if you're going to use the formula, you can just use it. If you're going to use the calculator function, you have to label your inputs. It's super important. You will get docked points on the AP exam and my tests if you don't label inputs. All right, find the probability that she makes 11 or less free throws out of 12. So x is less than or equal to 11. So this means she could make 0 shots. She could make 1 shot. She could make 2 shots. She could make blah, 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 all the way up to she could make 11 shots out of 12. So we would have to add all those together, and that would be insane. Think about the probability of x equaling 8. That was a lot of work just for one of those numbers. And we would have 11 of those numbers, actually 12 of the numbers, 0 all the way up to 11 to calculate. That's too much to write down. Don't do that to yourself. We can use the complement. We can do 1 minus the probability that she makes 12 because that's the only thing that wasn't included in 11 or less out of 12. And this is so much faster. So 1 minus 12, choose 12, times 0.85 to the 12th power times 0.15 to the 0 power. Plug that in your calculator. So again, 12 2's 12. So 12, and then go to math, over to probability, go down to NCR, and then hit 12 again. So that gives you that 12C12. Now that's 1. There's only one way she can make 12 shots out of 12, but I wanted to show you the calculator work again. All right, and then this is going to equal 0.858. Now, I can also use the binomial CDF function. So again, C stands for cumulative. So second, vars for distributions, hit the up arrow and go to binomial CDF. So I have the number of trials, n, which is 12. I have probability of success, which is 8.5. And then I have x, so my x value, and this is always x is less than or equal a number. So that's 11. That number is 11. All right, so 12 and 0.85 and 11 and enter. And I get the same answer, of course, 8577 or 858. Okay, so remember, if you use the calculator function, that's fine. Just label your inputs. All right, and last problem today, find the probability that she makes less than 3 free throws out of her 12 attempts. So probability that x is less than 3 would be the probability that x equals 0, or the probability that x equals 1, or the probability that x equals 2. So we're not including 3 because it says specifically less than 3. So there's only 3 ways to do this. You can use the formula. It's not too much writing, but it's a decent amount of writing. I'm going to use the binomial CDF calculator work because we want to save as much time as we can. It's important you understand the formula though. And then, so we have binomial CDF. So I'm going to go second, distribution, binomial CDF. And I have the number of trials are 12. My probability of success is 0.85. So 12p, oops, not 12, n and p. And then my x value is 2. Now I know it said x is less than 3, but the values are always included. So 3 wasn't included, but 2 is 2 or less. 2 is my x value. I'm going to hit enter, and I get 2.839 times 10 to the negative 7th power. That's what that e negative 7 at the end means. That means I have 0.000002839. That is a very small chance. All right, and then if you're in my class, there is one more page of notes, but it's just another example. So try it on your own, copy it in from our calendar, and that's it for today's lesson.